This is a video about angular momentum. Angular momentum is a quantity that tells us how hard it is to change the rotational motion of a particular spinning body, like this top. Objects with lots of angular momentum are hard to stop spinning or to turn. Objects with lots of angular momentum have great orientational stability. So basically, it's like linear momentum, except for objects that are spinning. Now we're going to look at two types of objects, but the equation for both of them is the same. It's this. The L stands for angular momentum. It's equal to I, which is the rotational or angular inertia, and the omega, you'll remember, is rotational velocity. The units for angular momentum are kilogram meter squared per second. So just remember, sometimes the word angular and rotational are interchangeable. Okay, so first let's look at a particle. The equation for the angular momentum of a particle is the particle's rotational inertia and its angular velocity. So when an object like this particle is spinning around this axis, we can calculate its rotational inertia using that equation. So first, we have to figure out that the rotational inertia for a particle is just mr squared. You'll find that on your equation sheet. Then what we do is we use this bridge equation to convert angular velocity to linear velocity. Then we plug that back into that equation, and then we do some algebra to find this equation. So this is the main equation that we use for the angular momentum of a particle. The angular momentum for a solid sphere is just as easy. It's I omega again, but in this case we would use the rotational inertia for the solid object depending on what solid object we're being given. So in this case it's a disk. We would use the rotational inertia of a disk, which is 1/2 mr squared, or for a solid sphere 2/5 mr squared, and so on. And then omega would be the rotational inertia of the solid sphere. The solid object. All right, so here's an example. Solid sphere mass 6 kilograms and radius 0.3 meters rotates about its vertical axis at a rotational inertia of 26.67 radians per second. The 2 kilogram particles attached to the outer edge of the sphere. So we got two objects here. We have the particle and the solid object. In this case, the solid object is a solid sphere. So first, to find the linear velocity of the particle, we need to use this bridge equation like we said earlier. So we take the 26.67 radians per second, multiply it times the 0.3 to get 8 meters per second to get the linear velocity. Then to get the angular momentum of just the particle, again, we plug it into this equation. You have to know where this equation comes from because it's not on your equation sheet. That's the 0.3 of the radius, 2 kilograms, that's the mass of the particle, and 8 meters per second is the linear the linear velocity that we got from the bridge equation. And we get 4.8 kilogram meters squared per second. That's the units for angular momentum. For the solid object, we're going to first have to find the rotational inertia of the solid object to answer the question, what is the rotational inertia of just the solid sphere? So the rotational inertia is 2/5 mr squared. Again, this is a solid sphere, so we have to know which equation to use. And again, you'll always be given the equation for the solid objects. So it's 2/5. Now it's 6 kilograms because the mass of the solid object, in this case solid sphere, is larger than the mass of the particle. And we multiply it times its rotational velocity, and we get 0.216 kilograms meters squared. Now that's just the rotational inertia, not the rotational momentum of the solid object. To find the rotational momentum, again, we use this main equation here. We figured this out just a second ago. The rotational inertia is 0.216 kilogram meters squared. the rotational velocity is 26.67 radians per second. Multiply those together to get that value, 5.76 kilogram meters squared per second. To find the combined angular momentum of the system, all we do is we add the angular momentum of the sphere, the solid sphere, to the angular momentum of the particle, and we get a total of 10.56 kilogram meters squared per second. So that's how we go about finding the rotational momentum of a particle, the rotational momentum of a solid object, and how we find their combined rotational momenta. We're going to be studying the law of conservation of angular momentum in class. But let's fill out your notes. The law of conservation of momentum states that the momentum of a system will not change unless an external force is applied. Okay, how would you change this statement to create the law of conservation of angular momentum? Well, what we would do is we would use the angular version of force, which we remember is torque. So angular momentum of a system will not change unless an external torque is applied to the system. So our angular momentum conservation law reads like this. The momentum before equals the momentum after. Here's the angular momentum method. We draw a labeled picture. We'll use components if necessary. We're going to determine the positive and negative directions. In this case, again, counterclockwise is considered to be the positive direction. We're going to use bar graphs. AP Physics C is going to have to use motion maps. We write a conservation statement like angular momentum is conserved. We have to describe the role of the internal or external torques. We have to say whether if there is a collision, we have to state whether it's inelastic or elastic and say why. We have to write out a general equation, and then we have to write out our specific equations using our inertias and angular velocities, and then we substitute and solve and include the right units. And then in class, we will solve some examples, and that's it.